what is the volume for the region described by, and then there's a series of inequalities. So 0 is less than or equal to 2 times z, which is in turn less than or equal to 3 times r, which is in turn less than or equal to 6. And it gives us some formulas for volumes. The volume of a sphere is 4/3 pi r cubed. The volume of a cylinder is pi r squared h. And the volume of a cone is 1/3 pi r squared h. Probably one or more of those shapes will be involved. So the options were 4 pi, 6 pi, 8 pi, 12 pi, or 24 pi. Survey says, anybody get an answer? 8 pi. Okay. So, well, how do we do this? Well, you have a string of inequalities. And if you have a string of inequalities, what should you do? Well, you should split them into parts. So you have 0 is less than or equal to 2z. Well, that says z has to be greater than or equal to 0. Oh, by the way, I should point out, we're in cylindrical coordinates. Now, what would have told you cylindrical coordinates? Z and r. You say, I recognize those symbols, z and r, that shows up in cylindrical coordinates. So we'd be like, okay, we're in cylindrical coordinates, no theta is involved, work in the RZ plane and spin. Okay, so the first inequality says z has to be greater than or equal to 0. The second inequality, 2z less than or equal to 3r, says z has to be less than or equal to 3 halves r. So there's this line, z equals 3 halves r. We have to be below it. The last inequality, 3r has to be less than or equal to 6, so that says r has to be less than or equal to 2, which means we have to be inside of there. Now you overlap these, and you get a triangle. That's your triangle in the RZ plane. To make your shape, you spin it. So you spin it around your z-axis, and now we're like, wow, woohoo, we have a solid. And what is it? Well, it's a cylinder with a cone that you've carved out of it. So how do you find your volume? You take the volume of the cylinder, subtract the volume of the cone. Now, in terms of dimensions, the height is 3 and the radius is 2. So the volume of the cylinder, 12 pi. The volume of the cone is 4 pi. 12 pi subtract 4 pi gives you 8 pi. And there we go. All right, good, good. Fun problems, fun problems. All these things we get to look forward to. Okay, today's thought for today. Problems worthy of attack prove their worth by fighting back. This is Pete Hine, who we'll probably have some more quotes from him in the future. He liked to write a series of poems called Grooks, which were basically nice sort of thoughts. And why do I like this one? Well, problems can be hard. Just because a problem is hard doesn't mean you shouldn't do it. You should try challenging problems, and they will challenge you. You keep going. So good problems will challenge you. In some sense, if the problems you're doing are so easy and you keep getting the right answers very quickly, you're kind of not doing the right problems. You're doing stuff that you're already good at. Challenge yourself. Give yourself good problems which will fight back. All right. So, today, our topic. What are we learning? Well, if we think about what we've done in the last few lectures, we've been talking about space. And we said, okay, so we now know how to describe space. And we have a couple of different ways to describe it. We're not going to spend a lot of time in cylindrical and spherical coordinates for a while, but they will make a big comeback later. So it's good to see them now, so that when we see them again, we're like, oh yeah, no problem. Okay, so in terms of space, we can now say we're good with location. Check that box. But now we have another thing. We're trying to build up to calculus. And we say, okay, well, what does calculus need? We need to say, okay, location, yes, but there's one other important aspect that's needed to do calculus. And the other important other important aspect is change. Okay, so the question is, how are we going to think about change? And we say, okay, well, what does it mean? I mean, what is change? Well, change really has two important aspects. When we talk about change, and especially as we get into higher dimensions, there's two important things. One change aspect is how much did we change, the amount of change, and then in which way did we change, the direction of change. Now you might say, well, wait a second, hold on. We never talked about direction before. Why are you bringing up direction now? Because we've always talked about change as an amount. But actually, you have talked about direction. You just sort of hit it really well. So when we're in single variable calculus, when we talk about direction, well, when there's only one dimension, your direction only can go one of two ways. So that's where your plus minus comes from. So plus and minus is really about orientation. It's about direction. So plus says, oh, I'm moving in a positive direction. Minus says, I'm moving in a negative direction. But we're going up into three-dimensional space now. We have so many more ways that we could change. And so we have to think about how are we going to represent change in our new three-dimensional setting. All right, so that's the goal for today. How do we represent change? We're going to start working with that object. And so the answer is we're going to use vectors. So vectors, this is our tool for measuring change. Now, we'll start by doing some intuitive things. We'll say, okay, let's think of the picture. Let's build up our geometrical intuition. So we have a vector will be represented by a line with an arrow at one end. Now, what does this mean? Well, the length of that line segment, that's the amount of change. And then the direction is you follow the direction of that line segment, right? Because it tells you how much there is. And you just have to be careful because it can be very sharp on those arrows attached. But okay, all right. Now, here's the thing. Points are sort of locked in, but vectors are not. Vectors are measuring change. So that is to say, if I move over a little bit, if I have the same length and I have the same direction, these are the same vector. So vectors are not tied to a specific location. Vectors are all about change. So these here are the same vector. But of course, if I have, say, the same direction but a different length, then it's not the same vector. Or if I have the same length but a different direction, again, not the same vector. So it's direction and length that determines your vector, and vice versa. So if we ever are in the situation like we need to find a vector, we ask ourselves the two questions: what is its length? What is its direction? And oftentimes, if we can answer those two questions, well, then life is good, because we definitely know the vector. Okay, so what are things we want to be able to do with vectors? Well, we have several important things. So we'd like to scale a vector, and to scale is to change length. So for an example, let's say if I have a vector v, if I multiply it by 2v, it's going to change the length by a factor of 2. And I probably should pause and say, when we talk about vectors, you'll see it written down in two different ways depending upon who does the writing, like on an exam or a quiz. So you'll either see it with a little arrow on the top, or you'll see it bolded. So that's just to emphasize what a vector looks like. But I'll try to follow the arrow on top today. So again, scaling, just multiply the length. What would half times v look like? Yeah, it's like half as long. What about negative v? What would that do? Yeah, it flips the direction. Same length, but in the opposite direction. Okay, so that's scaling. All right, so scaling makes sense. Stretch it, squish it, flip it around. If there's a minus, life is good. Okay, well, good. So that means we can do things like, oh, I could double the change, or I could half the change. Now, the other thing we might want to do is we might want to say, what about adding vectors? So it's like I have multiple things changing, and I want to do the net effect. All right, so adding. What can we do? Well, so we have, say, a vector v, and we have another vector, let's say, w. And throw the arrows on the top. How do we add two vectors together? Well, now we remember. We said, look, vectors aren't tied down. We can move them around. Say, okay, well, that's fine. So how do we use that to our advantage? Well, the idea is we'll start with v, just put it anywhere. And now take w and move it so that where v ends, w starts. So we'll move the end of w or the start of w, depending on how. All right, we'll just move w so that essentially we're linking them together. That's how I'll say it. All right, now I say I change by v, and then I change by w. So the v plus w, that's going to be their combined change. So if I have one change plus another change, then the net change is going to be what happens if I combine the start of v with the end of w. So this is v plus w. So that's how we add vectors. String them together. And it doesn't matter which order that we add vectors in. All right, great. So that's wonderful, but we like numbers. Okay, so how do we get to numbers? Well, we're going to think about some special vectors. Okay, so we have our three-dimensional space, x, y, and z. And we're going to identify three vectors, and we're going to call them I, and j, and k. Now, what are they? Well, I, j, and k are the following. They're I, it points in the x direction, and the positive x direction, length 1. And we'll talk about length 1 vectors in a few minutes. In the meantime, j points in the positive y direction, and it has length 1. And k points in the z direction, and it also has length 1. So we have these three basic vectors, I, j, and k. Now what we want to do is say, okay, can I somehow take a vector and rewrite it in terms of these three vectors, I, j, and k? Spoiler alert, yes. So, but picture-wise, how does it work? Well, we pick a point, any point. So suppose here I have a point, and we'll call it x1, y1, z1. And over here is x2, y2, z2. Now, what's going to happen? Well, what happens is I can think of there as being a box. So we have some change here in the z direction, some change in the x direction, some change in the y direction. So I'm going to throw a box here really quickly. imagine I can draw boxes without them looking very strange. Okay, so there we go. There's our box. Now, when we talk about a vector between points, it's a change between points. So in other words, I start at one point, I move to another point. And so we say, okay, so there's a vector between these 2 points. And so we draw that vector in. So here's our vector v. And what we'll do is we'll say, you know what we can do with vectors is we can add vectors together. Well, if we can add vectors together, we could also break vectors apart in some way. So I just need to find a sequence of vectors which has the same effect as this vector v if I string them together. Okay, well, here's one way to do it. We'll move purely in the x direction. Then we'll move purely in the y direction. And then we'll move purely in the z direction. So that I change my vector and I really break it into 3 steps. Only x, only y, only z. Now, the nice thing is, we say, hey, this vector that's pointing in the x direction has got to be parallel to a vector to any vector that points in the x direction. Do we know a vector that points in the x direction? I, yes. I points in the x direction. So this vector and that vector are parallel. Now, one thing I forgot to mention, I probably should mention, we'll come back here to this previous page, is that vectors which have the same direction are called parallel. So in other words, if I scale a vector, it's still parallel because it's still the same direction. But there's also the opposite is true. If you're parallel to each other, you have to be related to each other by scaling. So vectors with the same direction are parallel. Okay, so the punchline, this first segment of our journey, purely x direction, it's parallel to this vector I. So the only thing I have to figure out is how is it parallel? In other words, how do I scale it? Well, what do? I say, well, how much did I change in the x direction? Now I know the direction of change, I just have to figure out the amount of change. So in going in the x direction, I went from x1 to x2. So how much change was there in the x direction? x2 minus x1, the difference. So our vector v is x2 minus x1 times I. Now, segment 2, I move purely in the y direction. So I'm parallel to the vector j. So I just have to say, well, how much did I change? I went from y1 over to y2. So what was my change in the y direction?
y2 minus y1.
y2 minus y1. So that is y2 minus y1 times j. And probably you can see where we're going here. The last leg of our journey. We only change in the z direction. But how much? z2 minus z1. And since we're changing in the z direction, we're parallel and we can scale. We're using the fact that these have length 1. So we're just saying, okay, I just need to scale to get the proper length. I already know the length I started with was length 1, and so I get the amount. And so we have that our vector here is x2 minus x1i, y2 minus y1j, z2 minus z1k. And in particular, you'll notice really what we have is we have a change in x here, the change in y there, and the change in z. So if I want to understand the change, I can understand the change in each of the 3 directions, x, y, and z. We'll often write this using a shorthand notation in the following way. As x2 minus x1, y2 minus y1, z2 minus z1, but not with parentheses, but with these angled brackets. So this is a vector, not a point. So be careful with your notation. Be careful. What do I mean? Well, we can just sort of, what's the difference? What's the difference between 1, 2, 3 versus 1, 2, 3, where we went from parentheses to these angled brackets? Well, again, 1, 2, 3 is a very specific one location. How do you get there? Well, the answer is you move 1 in the x direction, you move 2 in the y direction, and you move 3 in the z direction. So it's a point. It's a one single point. On the other hand, what's the vector 1, 2, 3 look like? Well, it's anything where you change 1 in the x direction, 2 in the y direction, and 3 in the z direction. So it could be anywhere. It can happen in all sorts of places. All of these are the vector 1, 2, 3. Now, I will point out one thing very useful, and we will from time to time take advantage. If I start at the origin and I go out to the point 1, 2, 3, what vector comes out? The vector 1, 2, 3. So we will from time to time take advantage of that to say, well, one way I can think of turning a point into a vector is let me take the tail end of the vector and nail it down to the origin. And then I can get some connection. All right, so what do we need to do? Well, we need to be able to do the same things we talked about before. So we mentioned scaling, and we mentioned adding. So let's first off talk about scaling. How do you scale a vector? So in other words, I have a constant times the vector a, b, c. So remember, scaling says you have a constant times the vector, and you're stretching it or shrinking it, possibly flipping it around. Intuitively, what should you do? Yeah, someone said multiply a and b and c each by k. And that's exactly what you do. You say, okay, if I want to have a change, my vector a, b, c, and then I say, well, I want to have that multiplied by a factor of k, I just multiply the individual changes each by a factor of k. So scaling works pretty nicely. It works entry by entry. Nice. Nice. All right. Well, what if we don't want to scale? What if we want to, say, add? So I have a vector a, b, c. And I have another vector d, e, f. And I want to add those together. What do I do? What do I do?
Add the individual values.
Yeah, you add the individual entries. So I say, well, look, this first entry here is telling me how much x changes because of the first vector. On the other hand, this first entry tells me how much x changes because of the second vector. So if I want to get the total change, I add those two changes in x, which is a plus d. So it's like, wow, vectors work pretty simple. It's just entry by entry. Life is good. We can do that. All right, good, good. Now, one more thing. I'm going to jump back to this page, ask a question, and then we can get to our first example of the day. So we talked about scaling, we talked about adding. One more thing we'd like to do is magnitude. Okay, so right now, geometrically, how do you find the magnitude? Well, this is formula is if we have numbers. What if we don't have numbers? What do? You grab your ruler. You say, look, I just got to measure it. I go and find something to measure with. That's a ruler. But now if you have numbers, oh, good. Numbers. We like numbers. All right, what's the magnitude of a vector? And so we're going to write this magnitude, we use absolute value signs. Why do we use absolute value signs? Well, because absolute values actually mean something slightly different than what most people think it means. You usually think absolute value says, oh, you just get rid of the sign. Make it all positive. That's what absolute values mean. But absolute value sign is really a shorthand for size. So it's like, I want to know the size of this. So for vectors, when I talk about the magnitude of a vector, it's what's the size of the vector? All right, so how do we find magnitude? Well, what can you do? We can use the distance formula, absolutely. And how do we use that distance formula? Well, remember what we can do, we mentioned this already, just take the vector and you just nail down one end of the vector to the origin, and then you get that the vector ABC goes to what point? ABC. Then the length of the vector is the distance from ABC back to the origin. So what is that? By the distance formula, it's the square root of a squared plus b squared plus c squared. But if you also remember the distance formula, you might remember that we said, oh, the distance formula is the square root of change in x squared plus change in y squared plus change in z squared. And that's what these a, b's, and c's are measuring. All right, so we now have our basic rules. Any questions about our basics? Okay. Nice warm-up problem. A 40-mile-per-hour wind is blowing due south, also known as 270 degrees. And you are on a plane that has a bearing of north 60 degrees east. Okay, maybe we should draw some pictures here so we can follow along. All right, so we have a wind, and the wind is blowing, and it's blowing due south. Okay, so here's our wind. And you're on a plane that has a bearing north 60 degrees east, which is also called 30 degrees. So north says you start at north, and then you turn to the east, which is that direction, by 60 degrees. So that would be over here. And so this is our plane. So this is the way that the plane is flying. So we'll put some directions here: north, east, west, south. Now, what's happened? The bearing of the plane, in other words, you have the plane pointed in a certain direction. But just because the plane is pointed that way does not mean that that's the way the plane actually is moving relative to the ground. How is the plane moving relative to the ground? Well, the answer is it's pointing and going directly east, due east. Now the question, what is the airspeed of the plane, and how fast is the plane moving relative to the ground? Okay, now we should be very careful here in that we've drawn what looks like vectors, but we haven't drawn them well. Okay, so let's think about what's happening to our plane. So our plane is having two things that are changing its position with respect to the ground. One thing is how the plane moves through the air. That's the bearing of the plane and its speed, or if you like, its airspeed. What's the other thing that's affecting its position? The wind. And the wind is how is the air moving relative to the ground. So we have two things changing. The plane is changing relative to air. Air is changing relative to ground. When we add up those net changes, we get change of the plane relative to the ground. So we say, okay, so what do we have? Well, it's like adding vectors, right? So if our picture is a little bit more accurate, we have our plane, we have our wind, and then we have what's actually happening. So this is plane relative to air. This is our wind, This is plane relative to ground. So that's the picture. And you'll see, again, it's really a vector problem because it's the add up the changes of these two to get the net change. The third one. So good news. What do we have in our picture? We have a right triangle. Oh, happy days. Happy days are here again. We have other good news that we haven't put in our picture yet. What's not in our picture? We have some angles. Okay, do we know any of these angles? We know the 90, yes. And that's 30. And the other one is 60. Okay, good. Nice. Do we have any other information? Yeah, wind is 40 miles per hour. Now, what is this telling us, this 40 miles per hour? It's the magnitude. So this part, due south, is direction information. This part, 40 miles per hour, is a magnitude information. So we could say, hey, this vector, the one aspect is the direction, but the other aspect is the length. And notice, initially I put it here, but I can move it wherever I need it to be moved to. So that's why we can move it so that it lines up nicely. So we have a 30, 60, 90 triangle. We know one of the sides. Can we get the rest of the information? Yes. Do we know the hypotenuse? Or does anybody know the hypotenuse? It's 80. Yes. They might say, whoa, how'd you get that so fast? Well, if you copy a 30, 60, 90 triangle, what do you get? You get an equilateral triangle. That's half of the length of one side, and that's the length of the side. So this side is 80. Now that's, of course, if you know your equilateral triangles. If you don't know your equilateral triangles, what do? You use trig, right? So we can use trig to find, say, this side. So suppose we know this angle is 30, and we know what? The opposite side is 40, and we want to know the adjacent side. What relates an angle, the opposite side, and the adjacent side? Tangent. So tangent of 30 degrees is opposite over adjacent, which we don't know what that is. I didn't give it a name, so I'll put a question mark here. Now, do we know the tangent of 30 degrees? Yes, we do. What is it? Yeah, it's 1 over square root of 3. Good. Don't stress too much about memorizing the tangent of 30 degrees. So, our missing side is how long? 40 times square root of 3. All right. Now, the answers. What's the airspeed of the plane? What's the answer to that one? 80 miles per hour, because that is asking about this vector, the plane through the air, airspeed. And then the second question, how fast is the plane moving relative to the ground? It's moving at 40 root 3 miles per hour. And so even though it's moving through the air at 80 miles per hour, turns out 40 times the square root of 3 is less than 70, I think. Yeah, maybe it's near 70. So it's moving slower than you would expect it to. So that's why you don't like to fly into a headwind. It slows you down. All right, so we can add. Good. That's about as close as we'll get to doing a physics problem for a few months. I know you're disappointed. But physics, some of my favorite friends are physicists. Okay. So, we've talked about vectors. Now we want to talk about unit vectors. Now, the name unit vector probably is very descriptive, very suggestive. So when you see the word unit showing up, what do you think of? Or just uni as a prefix? 1, right? So like unit circle is a circle of radius 1. Our unicycle, well, that's something with just 1 wheel. Our unicorn is what's left in the field after you harvest, right? There's just 1 corn left, right? Anyways, okay, so the point here, unit is representing 1. And so when we talk about a unit vector, these are vectors with length 1. Now, why do we give these a special name? Well, if you know ahead of time that your vector has length 1, what's the important information about your vector? Direction. Because remember, vectors only have 2 things: length, or magnitude, and direction. So if you are told, hey, your vector has length 1, you're like, okay, well then it's just, all I care about is the direction of that vector. Okay, so why do we use unit vectors? Well, these capture direction information. Now there is a nice little fact that most vectors can be scaled to become a unit vector. In fact, there's one exception. There's a special vector, which we'll mention here. And it has a name called 0. The 0 vector. What do you think the 0 vector does? The 0 vector represents no change. So the 0 vector corresponds to a situation where no change has occurred. And I like to say it's the directionless vector because there's no direction it goes in. And I used to joke that, of course, the 0 vector was sort of the art history major of vectors. Just no direction in life. But I used to joke like that, but then it turns out that the dean of our college is an art history person. Don't report me. So, all right. So, okay, so unit vectors. Now, what can you do? Well, nice fact, if you have a vector v, so given a vector v, where it's non-zero, we can scale to get a unit vector. All right, so the question is how much? Well, the answer will not surprise you. You take 1 over the length times the vector. So if you take any vector that's non-zero and you divide by its magnitude, you get a vector which has length 1. So you can make unit vectors. And all right. So let's see. Let's try some problems here. Now, you might notice that my first vector seems out of place in that it only has 2 entries. I will say, while we're motivated by 3-dimensional settings, and there is a time, in particular, say next Friday is a great day, where we really need 3 dimensions. When we talk about vectors, it works in many different dimensions. So it works great for 2 dimensions, 3 dimensions, 17 dimensions. So we can work with vectors in any dimensions. So let's just pick some of these. We'll pick the first one, 3, 4. What's a vector which has the same direction, unit length? So what's the unit vector pointing in the same direction? How do you figure that out? So what's the first step? Find the magnitude. So what's the magnitude of the vector 3, negative 4? 5, because it's square root 9 plus 16. All right, and so what do you multiply it by? 1/5. Now, the question, can you leave the 1/5 on the outside, or do you need to have the 1/5 go on the inside? And the answer is yes. Either way, whatever's convenient. I tend to, if I see a fraction out here, I like to keep the number of fractions small, so I'd leave it on the outside. But if you prefer, you can move it to the inside. These are both the same vector. So whichever one you're more comfortable with. All right. Well, how about this vector? T squared minus 2, 2t. A first question for you, is this allowed? I don't have numbers in here. I have symbols. Can I do that? Yes. Yes, I'm a trained professional. Yes, yes. And in fact, we are going to be building up to the idea of what is known as vector valued functions at some point in the near future, where the entries can change. So yes, you are allowed to do that, and you're still allowed to ask questions such as, all right, what's going on? What's a unit vector that points in this direction? So what do? We find the magnitude, right? So it's the magnitude of the vector, t squared minus 2, 2t, which is the square root of t squared minus 2 squared plus 2t squared. Well, maybe things get nicer. T to the fourth. And then let's see, what's the cross terms? We have minus 4t squared plus 4 plus 4t squared. Ooh, that's nice. A little cancellation. A little cancellation never hurt anybody. So we end up with the square root of t to the fourth plus 4, which is also known as the square root of t to the fourth plus 4, because I can't simplify any further. That's as simple as it gets. Okay. So, what's the answer for the unit vector that points in the same direction? 1 over the square root of t to the fourth plus 4 times t squared minus 2, 2t. All right. And let's see, how are we doing on time? I don't want to make sure we have enough time left. Oh, we're running out of time. Okay. So I will say that this 3, negative 4, 12, the length of that, anybody see it off the top of their head? It is 13. So 1/13, 3, negative 4, 12. All right. Again, find the length. So there is another thing that we need to talk about, which is the notion of a midpoint. So what's a midpoint? Well, you kind of hear it, and you say, oh, I know what a midpoint is. A midpoint is a halfway point. It's halfway in between 2 points. So if I have 3, 4, 1, and over here I have 7, negative 2, 9, I can think of these as being 2 points, and I say, well, draw the line segment between those 2 points, and then put a point exactly in the middle. This would be the midpoint. Now, the question, how do you find the midpoint? Now, what's your intuition say to do? You add the points and divide by 2, right? Can you add points? No. Adding points is geometrically nonsense. But it feels right. Now, I'm going to tell you that the intuitive thing that you just mentioned will get you the right answer. But it's not justifiable. So we're going to justify it, though. So what do you do? Well, what can we do? We can say, let's look at the vector that goes all the way. We still have like 5 minutes. Don't get too anxious. I know it's a long weekend, but it's like, oh, come on. So what's the vector that goes all the way? Yeah, find the differences, right? 7 minus 3, minus 2 minus 4, 9 minus 1. So that's the vector that goes all the way from one to the other. So what's the vector that goes half the way? What do you do to that vector? Yeah, you divide it by 2. Say, okay, I just need to go 2, negative 3, 4. I scale by 2. So we're scale down by 2. So scale by half. And now, if I start at this point and I change by this amount, then I'll be at the midpoint. So now, where is the midpoint? We can write it down. It turns out to be at 3 plus a change of 2 gives us 5. 4 plus a change of negative 3, 1. 1 plus a change of 4, 5. In general, it's exactly like you think. It turns out that if you just add the individual coordinates and divide by 2, it is the midpoint. All right. Well, I have some other examples. I will just scan those in because we have to finish with our multiple choice problem, which is always fun, right? Find the point P, where P is the point furthest from the point minus 8, 2, 4, and P lies on the sphere. X minus 2 squared plus y minus 7 squared plus z plus 6 squared equals 36. And there's 5 possible points. 6, 9, negative 10, 14, negative 17, 14, negative 2, 5, negative 2, 2, 7, negative 6, 8, 5, negative 14. The answer is A. How does it work? You have your point and you can get to your center. You just need to keep going how much further? You need to go 6 further. Well, you need to know which direction you're going, so how do you figure out the direction? That's where vectors come in. So you say, let's use a vector to figure out how much I changed. And pro tip, it's useful to scale things to make it easier to work with. You say, okay, this is in the direction of 2, 1, 2. That has length 3. I just double it. That says I need to go an additional change of 4, 2, negative 4 from the center, which gets you to 6, 9, negative 10. And that's the answer.